Dave, so you recently won a grant.
Yeah, that's right. So it's called a Prosperity Grant, and it's in partnership with Nottingham University and a large multinational company based in the US and the UK,
Lubrizol.
Lubrizol. And the object of the grant is to do chemistry in a more sustainable way. So it's all combined with, as I said, using a life cycle analysis for each one of the products. So then the starting materials, we use the ones that's got the lowest energy requirements, and that's sometimes from renewable resources, sometimes from petrochemicals, and because sometimes the monomers from renewable resources need more energy to extract or to grow, whatever, and so it's not always simple. So you need.
So you say oil may be more sustainable.
Some of the chemicals at the moment, some of the petrochemicals, are lower energy than some of the plant-based materials. Another issue is that you're convincing the farmer to grow chemicals and not food. In your mobile phone, there'll be something that requires a chemical to be made, and that chemical can only come from oil. You can't compromise on performance, right? But actually, there'll be enough oil to make that stuff for a million years, maybe. Unless we burn it all, then there won't be.
One of the solutions to make chemical synthesis more sustainable is to move from batch to flow.
Yeah, absolutely. And so we have a number of commercial plug flow arrangements where we can do photochemistry, thermal chemistry, and also electrochemistry, and also hydrogenating flow. But all of those, they're very good for laboratory scale, but when we scale up, we'll then have to really pay attention to the mixing. And then having the stirred tank reactors allows us to go from very thin tubes, which are essentially 0.16 millimeters in diameter, and gives us a total volume of 10 mils or something, and we are, which is fantastic for the laboratory, but then we're limited to how much we can go up. And as we increase the diameter of the tubes, the mixing in the plug flow will get worse. And so we need then to have the stirred tank reactors.
Yes, and at that point we worked together for how many months? For several months now. You have tested our reactor.
So we've used the stainless steel reactor, and we've used the new reactor, which has got which is transparent, so we can actually see what's going on inside. And what we've done, most of our work is polymerization, and probably outside of metallocene, the most common form of polymerization is free radical. So that makes things like polystyrene and polymethyl methacrylate and polyvinyl chloride, and very little of that is done in flow. And where it is, normally there's maybe 2 or 3 batch reactors in series.
Why do you need several reactors in series?
So when you make a polymer by free radical, you've got by definition, a dispersed product, and you have something called molecular mass, so dispersity, and the properties of the polymer are dictated by the molecular weight distribution, and the higher molecular weight polymers, which affect something called MW, will affect the mechanical properties. The stirred tank reactors in series, and in your case, you've got a number of them at very small volume going to the next one, which makes it very efficient, is that the dispersity can go from, say, 4 to around 2. So I know that's just a number, but what that means is that you've removed a very high molecular weight. You provide us this facility, which is very simple to use in a laboratory with very little training, right? And you can just switch from a batch reaction to the flow reaction very easily. So in general, most of the research we're doing, and we work with all sorts of industries, from personal care products to automotive, and just very diverse. Everybody wants more sustainable processes.
So you consider flow is the way?
Absolutely. So we need to think about sustainability in the whole sense. So we do need to think about using chemicals from renewable resources. We do need to think about the ones that the best life cycle analysis, and then we do need to think about the process that we use to convert them into the products. And Flowers allows us to do that, I think, with a great deal of versatility, but also allows us to have the feedback mechanisms and use algorithms and artificial intelligence from the online analysis and that informing the pumps on how to change, and then that will give us the real optimum reaction conditions.